Assalamu alaikum. So in last lecture we discussed various need of the DSP. What is the need of the what are the advantages, disadvantages of DSP? And basically, if I simply ask you that why we go for signal processing, what is the need for signal processing? See, what happens basically in a signal processing, in a signal processor, you are given a one type of signal. This signal enters the system and generates another type of signal. Fine. For example, I will give. Let me make you more clear with the help of an example. You are, for example, you are driving a bike. Fine. You press the bike. You press the brakes. What will happen? Its speed will decrease. Fine. So, the your pressing of your brakes is one type of signal. Fine. It it enters into the system, that is the bike, and what is the result is the your output is decreased. Let me give you a more simple example. For example, tomorrow, uh, when you will appear for the exam, fine, I will ask a numerical. Fine. So your I will ask a numerical. So my question is one type of signal. Fine. So it enters into the it's display. It will be displayed there in your question paper. That is the system. And whatever you get the output, fine. Whatever you will get the output, that is the other type of the signal. That is your solution. The other. For example, I will give another example. Turning the switch on of an electric bulb. What it does, when you just switch on the electric bulb, it's a one type of signal. Fine. This uh, it enters into the circuit and your lamp or the system. It enters the system or the circuit, and your lamp is illuminated. That is another type of signal. So it will get more clear when we take impulse response. I will show you the diagrammatically, because I can't make each and every diagram on the PowerPoint presentation. Inshallah, when there will be your class, I will take real-time classes in Islamic University. You will get you'll be able to visualize things more clearly. So, in the last lecture, we studied various need for the DSP and the classification of signals. So, just starting from that only. Right? Okay. So, what is in last class also I told you what is a continuous time signal. So this signal can be defined at any time instant. Fine. So this axis, you will see, this axis is continuous. Fine. So it can be defined at any time instant. So there is no break on this time axis. Whether I will take here, it has a value. Fine. So this time amplitude, this time axis is continuous. See, right, starting from right here to here, there is a value for each and every time instant. Fine. So that is continuous time signal. So this is what type of signal is this? Exponential signal. Fine. This is increasing exponential. This one is increasing exponential signal, and this one is decreasing exponential signal. So both are examples of continuous time signal. You just in continuous time signal, you just consider the time axis. Fine. This is also another type of continuous signal, considering the time axis, and it's a sinusoidal signal. Fine. Then you have discrete time signal. So again, see, amplitude is not considered in this. Whether amplitude is continuous or not, we are not. We are discussing the time axis. See, Here it's, for example, this is the time axis, fine. Here it is t1, it is t2, it is 3. Time is not continuous, it's splitted, fine. It is t1, it's t2. So here, so this amplitude, if you just see, the amplitude can be continuous, fine. But your this time axis, I have discussed this also in the previous class, but your time axis should is discrete. So that is a discrete time signal. So it's defined only at so it is defined only at discrete time, right? Then you have continuous amplitude signal. So now the amplitude variation is continuous in such type of signals. Now the amplitude variation is continuous in such type of signals, right? Now continuous amplitude signals uh, can be either discrete or they can be continuous in time. So we are not considering now the time, we are only considering the what? We are only considering the amplitude. Then you have the discrete amplitude signals. So these signals can take only discrete. Now we are considering the discrete. Now again, the time can be discrete or it can be continuous. Fine. For example, can you think of an example? Uh, see, see, this is a continuous amplitude signal. This one. Amplitude is also continuous and time is also continuous. Fine. So this is a continuous amplitude signal. You see, there is no break in the amplitude. Fine. Whereas this is a discrete amplitude signal. Now there is a break in also in the amplitude. It's having different amplitude levels. See, if I join this to this, right, it's a different amplitude. It's one, right? It's another amplitude axis. It's another amplitude. It's another amplitude. Right? Likewise in this also. See, this is discrete amplitude signals. So these signals take only discrete amplitude values. Fine. Again, the discrete amplitude signals can be either continuous or discrete. Fine. Now, what are discrete signals? So I discussed continuous time signals and discrete time signals, followed by continuous amplitude signals and discrete amplitude signals. So in continuous amplitude, you have the amplitude that is continuous, and in discrete continuous time signals, you have the time that is continuous. Right? Similarly, in discrete time signals, you have the time that is discrete, and well as in discrete discrete signals. Fine. You have the signal. Now, what are discrete signals? What are discrete signals? So these signals which are discrete in time as well as amplitude. So these signals which are discrete in time as well as amplitude are digital signals. So can you think of an example? So the signal representations in computers and digital signal processors, right? They all use digital signals only. The digital signal can be what? It can be binary, fine. It can be octal. It can be hexadecimal. It can be hexa. It can be 16-bit, fine, or 32-bit, or even 64-bit. Then you have the analog signals. So the signals which are continuous as well as the signals which are continuous in time as well as amplitude. They are analog signals. For example, the exponential signals and the sinusoidal signals. See, the exponential signals, and the same. This is continuous in time as well as amplitude. So these are what? Analog signals. Same is the case with this one. So it is also continuous in time, as well as it's continuous in amplitude. There is no break in amplitude. You see, there is no break in the amplitude, right? So it's continuous in time as well as continuous in amplitude. So it is analog signal. Has there been, see, if it's discrete in simple, no confusion. If it is discrete in time, then you have the discrete time signal. If it's discrete in amplitude, then you have the discrete amplitude signal. If it is discrete in both, that makes it a discrete signal. Same is the case with analog signals. I hope it's clear. Right? Now you have the deterministic signal. Now, what are deterministic signals? Now, a signal which is completely described by the mathematical model is called deterministic signals. Fine. The value of the deterministic signals you can evaluate at any time instant, for be it past, be it present, or be it future, without any uncertainty. Fine. So I have also given an example. Again, a sinusoidal signal, xt is equal to a. So you can model it mathematically. Fine. You can analyze it, fine, with the help of mathematical problems, mathematical formulas, right? It's defined for every interval. It is defined by some mathematical rule. It follows some mathematical principle, right? So it is known as deterministic signal, right? Next, you have the random signals. So these signals which cannot be described by the mathematical model are called as random signals. For example, can you think of an example? The noise signal or the speech signals, they are all random signals. Now the random signals cannot be described. Now see, random signals cannot be described with the help of mathematical interpretation, mathematical rules, mathematical formulas. So what you need statistical properties, like, can you think of the PDF, probability density function, and all these all things? Fine. The probability PDF of continuous this function. So there you use the probable values, because you can't take out the exact or the accurate values. So you use the most probable values to describe those signals. So those signals are random signals, right? So this is a random signal. Example of deterministic signal is any of that sinusoidal signal, fine, that I showed you in the past, in previous one or two slides. So it be it sinusoidal, be it exponential signal, which follows some mathematical rule, mathematical law. Fine. Random signals, they cannot be described by mathematical models. Fine, they are random signals. For nice, speech, etc. and etc. They are all random signals. So this is an example of a random signal. Fine. So as you can see, it follows no mathematical law. You cannot describe it with the help of mathematical rule, particular mathematical rule. So you use probability in order to describe these kind of signals. Okay. Now you have multi-channel signals. Now what are multi-channel signals? Now when different signals are recorded from the same source, they are called multi-channel signals. For example, can you think of an example? See, ECG signals can be recorded in, you have different leads to record an ECG signal for the same person. It can be recorded in 3 leads, 12 leads, 16 leads. So you have different leads. So what this results in 3 channel or 12 channel ECG signal. So what is so you get source is the same, but you get different signals from a single source. So they are multi-channel signals. So what is it used? Multi-channel signal is used in studying correlation properties of the source. Right? Then you have multi-dimensional signals. What are multi-dimensional signals? Yes. So when the amplitude of the signal depends upon 2 or more independent variables, it's called multi-dimensional signal. Can you think of an example? For example, the intensity or the brightness at any point in the picture or image is a function of its x and y. Similarly, you have a graph. It depends upon. See, don't get confused. You have a graph. It depends upon x. X is one factor, be it light, fine, and y is be it intensity, fine, or luminosity, fine. So it is depending upon two factors, two conditions. Here you are not in multi-channel signals. You are considering the source. Source is same, and you get different type of channels from the same source. In multi-dimensional, you are considering two factors upon which the amplitude of the signal depends. So then I have given an example. Right? I hope it's clear. Okay. Now you have to study before heading into discrete time systems. You have to understand some standard discrete time signals that will be you discussing. These are important. This you all have studied in signals and systems. So those of you who have studied well, for them it's just a revision. These 5-6 video lectures, for them is just a revision of the previous curriculum of the signals and systems. Okay, now, so what is a unit sample sequence? So let's first me show you uh, this diagram. So its value of unit sample signal it's that type of signal which has a value whose amplitude is 1, which has a value of 1 at 0 sample instant, fine. Apart from that, it is 0 throughout, fine. So its amplitude value, fine, it's this value, amplitude value y-axis value is 0 throughout. So it is 1 only at 0 sample instant, fine. So this is the mathematical interpretation of this. So it is represented by delta n. The unit sample sequence is represented by delta n or del n, or you can also call it delta function, fine. So it is defined as delta n is equal to 1 for n equal to 0. What is n? Is the sampling distance, fine. It is 0 for n is equal to, apart from that, throughout the axis it is 0 for n is equal to 1, maybe it 1, b2, b3, fine. So it is 0, it is 1 throughout. So it is, see, it is 0, it is 1 for n equal to 0, and it is 0 for n not equal to 0. There is a typing error. Here it is for n not equal to 0. It's not n equal to 1. See, from the diagram it's very clear. See, it is equal to 1 for n equal to 0. There it is equal to 0 for n not equal to 0. It is equal to 0. See, on this point, on this, what is not equal to 0? This point, this point, this point, 1, 2, 3. So on all these points it is equal to 0. Only at 0 it is equal to 1. See, here it's a typing error. So here it is n is not equal to 0, not n is equal to 1. So how mathematically you represent it like this. So what does this arrow represent? This represents the 0th sample. So it means that at this place you have the 0 sample, fine, and that is equal to 1. That is equal to 1. Here you please correct it, because now it's already I am recording the voice, so I can't change it now. So but here it is n not equal to 0. Okay, so in next lecture we will discuss other standard discrete time signals. That's all for now. Assalamu alaikum.